Hello everyone, welcome back to another video. This is Pranav, and in this video we'll be talking about the topic hidden Markov model. Hidden Markov model is a statistical model used in various fields including speech recognition, natural language processing, bioinformatics and more. So HMMs are particularly well suited for problems involving sequences and their time series data. So the model is named hidden because it involves two interrelated stochastic processes, that is, one is the observed sequence and the other one is the underlying sequence of hidden states. And here are the key components and concepts of a hidden Markov model. First one being states, that are the hidden states. HMMs consist of a set of hidden states which are not directly observable but affect the observable data. The hidden states form a Markov chain, meaning that the probability of transitioning from one state to another depends on the current state and not on the previous states. And the second one is observation, that is the emission probabilities. So each hidden state emits an observable symbol or data with certain probability. So these probabilities are represented by the emission probabilities, and in some applications these are also called the emission probabilities or output probabilities. Coming to the third one, that is the initial state probabilities. The model also specifies the probability distribution of starting in each hidden state at the beginning of the sequence. And the fourth point being state transition probabilities, that is HMMs define the probabilities of transitioning from one state to another, and these transition probabilities can be represented in a transition matrix. The core principle of HMM is that it generates a sequence of observable data points by moving between hidden states over time, and the sequence of hidden states is not directly observable, but it's inferred from the observed data. And HMMs are used for a variety of tasks, that is speech recognition, that's to recognize spoken words or phonemes from audio signals, in natural language processing as a part of speech tagging, and named entity recognition and other sequence labeling tasks. Coming to the third one, that is bioinformatics, it also is useful in analyzing biological sequences such as DNA, RNA, and protein sequences for gene finding and sequence alignment. And gesture recognition is also one of them, wherein tracking, recognizing and tracking gestures in computer vision applications. And the last one being finance. So, modeling finance time series data for applications like stock market analysis, wherein you don't know the hidden data or the upcoming transition elements. So, inference in HMMs typically involve two main problems. That is, the first one being forward algorithm. So, forward algorithm is computing the likelihood of observing a given sequence of data, and the second one being Vitaby algorithm, which is finding the most likely sequence of hidden states given a sequence of observations. So this is useful for various tasks, and training HMM often involves the Baum-Welch algorithm, which uses the expectation maximization algorithm to estimate the model parameters from a set of training data. And hidden Markov models are powerful tools for modeling and making inferences about sequential data, but they do have a lot of limitations such as Markov assumptions. That is, states only depend on the previous state and not on the states that have already occurred, and which might not always hold good in real world scenarios. So coming to the main structure, that is prediction of weather for next day based on the current day's weather using HMM. So the particular code imports the NumPy, Matplotlib, and Seaborn and the HMM library. So here you can see the Python code for importing all those four libraries as mentioned, and that is from HMM learn we import the HMM library, and the other three libraries are to support these functions. And Matplotlib is majorly used to plot the figure, and we'll be seeing that in the final slide. And NumPy is used to store all the states in a NumPy array. So defining the model parameters. So in this example, the state space is defined as a state in which the list of two possible weather conditions, that is sunny and rainy. The observation space is defined as observations, which is a list of two possible observations, that is dry and wet. So the number of hidden states and the number of observations are defined as constants. In the code, you can see that states are taken as an array wherein you have sunny and rainy, and n states is the length of states, that would be two. And we print the states, and you can see the output as well. Similarly, we take observations as dry and wet, and the observations are also printed using n observations and len observations. So the start probabilities, transition probabilities, and emission probabilities are defined as arrays, and the start probabilities represent the probabilities of starting in each of the hidden states. The transition probabilities represent the probabilities of transitioning from one hidden state to another, and the emission one represents the probabilities of observing each of the outputs given a hidden state. The initial state distribution is defined as state probability, which is an array of probabilities that represent the probability of first state being sunny or rainy. The state transition one is defined as the transition probability, which is a 2 by 2 array representing or 2 cross 2 matrix that is representing the probability of transitioning from one state to another. And the observation likelihoods are defined as emission probability, which is a 2 cross 2 array as we just said, and that represents the probability of generating each observation from each state. So here we can see that the state probability, that is numpy array, that is zero point 0.6 and zero point 0.4. This is nothing but as we move from one state to another, what is the probability for the next one to occur. That is, it could be 60% or 40%, and we print it out, and that would be our array, and this numpy array. And the second one being transition probability, that would be a 2 cross 2 matrix or a 2 cross 2 numpy array. That would be 0 0.7, 0 0.3, 0.3, and 0.7. That is, you can take it as sunny and the rainy day. So when you see the probabilities, this is how it is printed. And similarly for emission probabilities, that is from one hidden state to another, these are the probabilities that we are going to take, or that we are going to define, and we are just going to print it as an numpy array. And so we create an instance of the HMM model and set the model parameters. So the HMM model is defined using the HMM.categorical HMM class from the learn library, and an instance of the categorical HMM class is created with the number of hidden states that is set to n hidden states. That is the variable that we are going to declare, and the parameters of the model are set using the start probability and transmat and emission prob. So these are the attributes to the state probabilities, and state probabilities, transition probabilities, and the emission probabilities respectively. So all those are declared in this code, as you can just see. And model.stats are model is used to configure all these values into the machine learning model that we are going to train for HMM. So defining an observation sequence. A sequence of observations is defined as a one-dimensional numpy array. That is, the observed data is defined as observation sequence. You can see that in the code as mentioned over here, and which is a sequence of integers representing the corresponding observation in the observations list. So we are going to reshape this. That is going to be in this particular format, and we print it out. Coming to the prediction part, so it predicts the most likely sequence of hidden states. That is, the most likely sequence of hidden states is computed using the prediction method of the HMM model. And we have declared something called hidden states, and we do model.predict, that is for the HMM model, and we print out the observation sequence. So once we print it out, the most likely hidden states sequence is printed out as an array, that is, you can see 0 1 1 1 and 0 0. So for this we can decode the observation sequence. The Viterbi algorithm is used to calculate the most likely sequence of hidden states that is generated, uh, and using this method we can decode the model, and the method returns the log probability of the most likely sequence of hidden states and the sequence of hidden states itself. So here we can see two particular values, that is the actual sequence and also the log probability, and This helps us plot the graph for a better understanding, and also the particular performance of the model too. So here we're going to plot the results for our HMM model, for which sunny or rainy is our state, and you can see that 0, 1, 1, 1 and 0, 0 are the states, that is our probability states, and this is the log probability. Using the log probability we are going to print this particular graph, and this would be our output. So by this way we can understand the working of HMM model. Hope you guys understood the concept, and thank you guys for watching the video.